The mission of particle physics in the first place is to unravel the fundamental building blocks of the universe and of all that surrounds us in terms of forces and interactions of particles. Then in order to do that, what we need is a lot of high technology. My research at Purdue is situated at 3 different topics. So we have composites and detector mechanics. Then we have also the science, the analysis of the data that comes out of the compact muon solenoid experiment, which is over at CERN. And the third one is to leverage AI and ML, the latest in artificial intelligence and machine learning, including quantum computing aspects, in order to analyze the vast data sets that we have. What makes quantum research at Purdue unique is the interdisciplinary aspect of quantum research, which is just not one unique discipline or field, but we have physicists, engineers, and computer scientists work together in order to harvest the benefit of this cutting-edge new field, which is quantum computing. And the benefit of that speaks and works together also with industry partners, where we have internships for students. So we have more than 100 students that go through the research groups, and they do applied physics and search for applied solutions for current real-life problems that we can solve, not just foundational physics questions.
Here at Purdue, we have a very unique ecosystem. You have people that are interested in working on the building the quantum computer, and also people who are interested on how to use the quantum computer. And so being able to interact with these different people is very unique. We use AI and machine learning to better understand the data that's being produced at the Large Hadron Collider, whether that's in analyzing the signals that are in our detector. We're working at even higher level output of trying to look at the events and see what kind of events took place.
The research group of Dr. Jung at Purdue is deeply involved with the phase 2 upgrade of the CMS tracker detector for the high luminosity LHC, and also with the physics analysis, in particular focusing on the measurements of top quark polarization and spin correlations, and also on the measurement of quantum entanglement and other quantum observables using the data that we collect with the CMS experiments at the LHC. Currently, I am the run coordinator of the CMS experiments, which means I am responsible for the operation of all the CMS detectors during the data taking and commissioning periods. In the next months, we will finish the round 3 of LHC, and we will start the long shutdown 3. We will need to be ready for the high luminosity LHC. So one very important item is to make sure the detector upgrade will proceed on schedule, and the Purdue group will need to make sure that, for example, the BTST will be ready on time.
We are working at the tracker integration facility here at CERN as part of the CMS experiment, commissioning and validating the barrel timing layer and tracker support tube. It is a carbon composite structure that enables supporting all of the silicon trackers that form the heart of the CMS detector for the high luminosity upgrade. So one of the support structures also enables us to flush the inner volume with dry gas to ensure that we do not have humidity and condensation on the silicon modules themselves. We also do a lot of research on really thin, ultra lightweight support structures with thermal pathways integrated into the support structures, not just for the high lumi LHC upgrade on CMS. We also have a detector R&D collaboration and mechanical design responsibility for the electron-ion collider coming up at Brookhaven National Labs that is conceptualized and is currently in the design phase.
A number of different engineering challenges arise as we build these often large-scale structures that have to meet extreme precision requirements. Typically, composite materials and composite structures aren't developed in a way where a meters-long structure has to be precise within sub-millimeter precision, but here in these applications it does. That's a challenge on the manufacturing side to make sure that our processes account for the shape change that occurs in composite structures. And then it's also a challenge on the measurement side. We have to then measure and validate and prove that we have made structures that are meeting these extremely tight tolerances. At Purdue and in the other programs that I work with for physics particle experiments, there is almost no wall between the physicists and the engineers. The engineers and the physicists have to be on the exact same page during the design, prototyping, testing, validation, and production phases of these projects.
We have physicists, we have engineering, we have computer scientists, and all of that comes together with a very large group of very talented young students. So that is where we want to harvest the promise of future workforce development with all of these cutting-edge tools. So we have a large pool of that drives really innovation at Purdue, and I would think establishes Purdue as one of the leaders in this field in the coming years.